Okay. So I want to keep our discussion concrete. So let me just begin with an example. Consider the matrix 3 halves, 1 half, 1 half, 3 halves. So this matrix is a linear transformation. This matrix represents the linear transformation that sends, let me get some colors. That sends the vector 1, 0 to the first column, 3 halves, 1 half. So I guess I'll look something like that. And that sends the vector 0, 1 to the second column, 1 half, 3 halves. So this is what the transformation does. And you might look at that and be like, well, what kind of transformation is that? That's not very interesting, right? But we know that since this matrix is symmetric, that is, if you call this matrix A, you have that A transpose is equal to A. Well, being symmetric is a special case of being normal, right? So if you're symmetric, that implies you're normal. Because we call a matrix normal if A conjugate transpose A is A conjugate transpose. Since this is a real matrix, this condition would just be A transpose A is A transpose. But since A and A transpose are the same thing, both sides just become A squared, right? And since it's normal, we have by the spectral theorem that we can write A as U d U conjugate transpose, where U is a unitary matrix. That is, the columns are an orthonormal basis, and D is diagonal. Well, now, recall, we've only proven this so far in the case where A is a matrix inside of a square matrix with complex entries. But if you're real, it's a special case of that, so it still applies. So you can do it to this matrix. You can write A in this way. And in fact, we already saw this example, I don't know, like last week. I think this is how I introduced this whole section, where I actually gave you the decomposition. It came out to be root 2 over 2 minus root 2 over 2, root 2 over 2, root 2 over 2. Yeah, I think it's my first matrix, yep. My D was the matrix, let me double check, I get the entries right. 1, 0, 0, 2. And then here I should have the conjugate transpose, it's real, so it's just the transpose. Root 2 over 2 minus root 2 over 2, root 2 over 2, root 2 over 2. And so this is my matrix. A can be written in this way. Check that, yeah, indeed, these columns form an orthonormal basis. So if you multiply him with himself, you dot the first column with himself, you go 1. Same thing with the second column. But if you dot them together, you get 0. But what this is really doing is it's giving you a story. You should think geometrically. What this is saying is there's an alternative way that you can think about A. You should think about this unitary matrix as a change of basis matrix, right? And this is just the inverse of that change of basis matrix. And then here you have a diagonal matrix. And so what we can do is instead of the story here where we just think about A as looking something like this, instead I'm going to imagine there'd be an alternative story down here where this step will be given by D, and then I'll have to do these steps. So let's check. I want this to be A, so I want A to be equal to this composition of steps. So the rightmost step is the thing I'll do last, so it should be this first guy. It should correspond with U, and this first step should correspond with U conjugate transpose, which for us is just U transpose, which is the same thing as U inverse. So U represents some change of basis from here to here, right? Or going up. U is changing the basis going up, whereas U inverse would be reversing that change of basis coming down. So one way to think about that is here, if you take the elementary vectors, 1, 0, and 0, 1, going up is just the change of basis U. So that's this change of basis. So that's changing the first 1, 0 into this vector, root 2 over 2 minus root 2 over 2. So it's changing it into this vector. And the red vector is getting changed to the second column, root 2 over 2, root 2 over 2. And so what we're really being told is we should be tracking these vectors, the blue and the red vector, not the green and the orange, but the blue and the red. Because if we look at how the story develops with the blue and the red, well, first we apply this. That's going to change it back to just the elementary vectors. Then we're going to apply the matrix D. What does D do? Well, it takes your first guy, the blue guy, and multiply it by a factor of 1. So blue just stays the same. And it takes the red guy and multiplies it by a factor of 2. So what was 0, 1 becomes 0, 2. And then you apply your change of basis again. So that's just going to rotate it back down again to this guy. Right? So what we're really saying is, since A is a normal matrix, we're able to represent this transformation as just being some change to an orthonormal. So here we have an eigenbasis that's an orthonormal collection of vectors. And so you can have some orthonormal, that is, these are unit vectors that are orthogonal to each other, and just keep track of how they scale. And that tells you the full story of the transformation. And in some ways, by describing the transformation in terms of this red and blue vector, I think it's quite a bit nicer to try and describe it with the green and orange one, right? You kind of see what's going on better. Everything in the blue direction stays fixed. Everything in the red direction doubles, right? Okay, so that's what we're saying. So you might want to always be able to tell a story like this. And you're like, oh, isn't the spectral theorem always letting us tell a story like this? Well, careful. What if I have an ever so slightly different example? So what if I have A, I'm going to make it very simple, 0, 0, 1, minus 1. No longer is it symmetric. What kind of matrix is this now? This is a skew symmetric matrix. That is to say, A transpose would be, well, you'd be switching the minus 1 and 1, which is just switching the sign of the overall matrix. A transpose is minus A. But skew symmetric matrices are still normal. This is still an important class of normal matrices. So you still have that A conjugate transpose A, that's just A transpose A, is A conjugate transpose. Since we're real, that's just A transpose, because both sides just come out to be minus A squared. And so you can still apply your spectral theorem. So let's do it. So we can say, okay, first of all, let's identify the eigenvalues. So my eigenvalues are going to be solutions to my characteristic polynomial, which is just the determinant of a minus lambda I. So that's just the determinant of this guy with minus lambdas along the diagonal, which just comes out to be lambda squared plus 1. Uh-oh. What are the roots of this? Lambda is plus or minus I. Let's go ahead and find the corresponding eigenvalues. So if lambda is positive I, we want to find solutions to a minus I identity times v is 0, right? So we find the corresponding eigenvector. And so here we get, let me just call this a v1, because I want to keep track of different eigenvectors. So here I'm going to get minus I, 1, negative 1, minus I, times, let's just say the entries of this is something like xy, is 0, 0. I get two equations. One is minus I x plus y is 0. The second is that minus x minus I y is 0. But these are actually redundant. The second equation is the first equation times I. Right, times I, this first guy. You get the, times negative I. Do negative I times the first guy. You have positive I squared, which is negative 1, and minus I. So these are redundant equations. So we don't need the second one. And so we just have that your y must be ix. That is, your vector v1 must be some scalar copy of 1i. Right? You can scale it by whatever you want, but that's what your eigenvectors look like. That correspond to I. And then if I go over here and I think about what happens when my lambda is minus I, I'm trying to now solve a plus I identity times whatever your second eigenvector is. Should be the 0 vector. So you just get I1 minus 1 I times some values xy is 0, 0. Hence ix plus y is 0, and the second line gives you minus x plus iy is 0. Maybe I'm beating a dead horse, but these are actually the same equation. You just multiply the first one by I to recover the second one. So this is redundant. So you just have that y equals minus ix. Hence, your v2 should be something of the form 1 minus I, and you can scale it however you want. Note, we get for free that these are orthogonal to each other, that your v1 and your v2 are orthogonal to each other. Right. Since you have a normal matrix, one of the implications of the spectral theorem is as you're finding your eigenvectors for distinct eigenvalues, you already get that they're orthogonal. All you need to guarantee is that they actually form an orthonormal basis. So how do we get into form an orthonormal basis? Well, we want to scale them, right? It's like, well, this doesn't have magnitude 1. What is the magnitude of this guy? Well, recall when you have complex entries, the way you find magnitude is so the magnitude of like v1 is the square root of that guy's conjugate transpose with himself. You're dotting them, but you're taking the complex conjugate of one of them. And so it just becomes the square root of 1 times 1 plus I times minus I, which is really important because if you didn't have the minus I, if you hadn't taken the complex conjugate, you would have got that its length is 0, which doesn't make sense, right? So its length is root 2. And so we can normalize this. That is, we can scale it to a unit length by dividing by root 2. And similarly, this is also length root 2. So we'll also normalize this by dividing by root 2. Okay, so what do we have? We have that I can now write my A, which was 0, 1, minus 1, 0, as, so this is my A. I want to be able to write it as some U, D, U conjugate transpose. And what does it become? Well, my D is just the values I and minus I. And my unitary matrix is, well, I'm scaling by 1 over root 2 of this guy. So it's 1 over root 2 of the first column is 1I, and the second column is 1 minus I. And then conjugate transpose over here. So again, I'm scaling by 1 over root 2, but I have 1 minus I. This I comes up as minus I. This stays down here as minus I. Now I have a 1. There we go. But here's the problem. If I want to say, well, doesn't this tell us a nicer way to tell the story? It's like this matrix A is just telling me that, let me get my colors, that the vector 1, 0 goes to 0, minus 1, and the vector 1, 0 goes to 0, 1 goes to 1, 0. It's like this is a rotation matrix. Yeah?
Shouldn't one of those i's be constant?
Oh, conjugate transpose. You're right. This becomes, it's the complex conjugate of the minus I becomes I. And the complex conjugate of that I was minus I. Very good. I took the transpose, so he moved up here and became negative. The 1 came down. The minus I stays where it's at, but it's positive I. Good catch. So this A is just the rotation matrix, right? You're just rotating by 45 degrees, or pi over 4, clockwise. But you're like, well, why can't we do a similar thing as before? Where there's some nice orthonormal, you know, it's like, well, there is, but it's imaginary. Maybe this was much too long to belabor the point, but in this decomposition, there's nothing that says that these matrices have to be real valued. When we proved the spectral theorem last class, we proved it with some matrix that has complex values. And it's fine if you pick something that happens to begin with real values. But even if you begin with real values, you're not guaranteed that this U and this D ends up with real values. You might have that the U and the D end up with complex values. Right? So it's like, in this case, when we decomposed it in this way, looked at the spectral decomposition, we got imaginary values, both in D and in U. Whereas over here, it all came out to be real. So, you know, this might be a little bit upsetting. You might want to say, if I start out with a real guy, I want to know when can I decompose it so that it ends up all being real, instead of a case like this, where I end up decomposing and have these imaginary guys, because it doesn't help me draw in the picture in R2. I can draw a corresponding picture here, but it has to be with C. You know, you'd have to do it with Cn instead of Rn. Okay. You understand the point, the problem, the concern? So what I want to do today is I want to strengthen this theorem to say, let's just begin with matrices that have real entries. But then what does my condition need to be on A so that I end up with matrices that still have real entries? That when I decompose it, it's still real. Because if I just let A be normal, well, I may decompose and end up with guys with complex entries. This was a normal matrix. It was a skew symmetric matrix. And it ended up with guys that had non-real entries. So you tell me, like, well, why did this one work and gave us all real entries when we decompose it, and this one didn't? Like, what's the difference between these matrices? And it's like, well, this one's symmetric, this one's skew symmetric. So maybe like a really naive guess would be, as long as you limit yourself to symmetric matrices, then when you decompose it, it'll all work out to have real values. So that should be your guess, because it turns out that's correct. So what I want to talk about for the rest of class is what I'm going to call the real spectral theorem. And so we're going to spend the rest of the time proving this, which just states that if you begin with A not just being normal, but being symmetric, if you're given some symmetric, I feel like the word symmetric should be a palindrome, right? Like that, they should name it something that's a palindrome, like simis or something. If you have some symmetric A with real value entries, so by saying A is symmetric, I'm just saying that A transpose is A. Then we already know, you already know, since it's symmetric, it's normal. So by the spectral theorem, you already know that you can write A as some U du. The content of this new theorem, of the stronger theorem, is that these are all going to be real. So since this is real, you just have to do the transpose. So then A is equal to this guy, where U is unitary and real, and D is your diagonal matrix and real, where these entries, or these matrices have real entries. Actually, it's stronger than this. It's actually an if and only if. Goes both ways. Same as normal. A matrix is normal if and only if. You can write it like this in general, with complex entries. But if you want to insist on entries being real, then you get that your matrix is symmetric. So one direction of this is very easy, so we'll do it in like 2 minutes, and the other direction will probably take us, several minutes, probably the rest of class. So here's my proof. What I want to argue is, like, if you want to end up with this having all real values, then you have to start with something that's symmetric. So I'm going to prove the backwards direction, right? So suppose you have some matrix A that decomposes as U d U transpose, where your U and your D are both n by n matrices with real values. Then I want to argue that A has to be symmetric. And to argue that, you just check that when you take the transpose of this guy, you end up with the same thing. So let's just do it. Like, what is U d U transpose? Transpose. That is my A transpose, right? It's going to go and show you that this ends up being A. So how do you do the transpose of a product of matrices? Well, you reverse the order and then you transpose each one. So U transpose goes first, but then it takes transpose, so it becomes U. D is still in the middle, but now it's D transpose. And then U is at the end, and now it becomes U transpose. Oh my, that's almost exactly what I started out with, except now I have D transpose. But what is D transpose? It's just D. So that's just U, D, U transpose, which is A. So like, that couldn't be easier, right? If you want them all, when you decompose it all to be real, you're going to end up with having this property that it's symmetric. The other direction, though, is a little more tricky. So let's try and go the other way. And I think to go the other way, I'm going to break this up in a couple steps. So ultimately, I want to get that my D has all real entries. So that means I want all my eigenvalues to be real. And then I want U to be real as well. So that's saying that I want the eigenvectors corresponding to my eigenvalues to be real. Or at least I can find some eigenvectors corresponding to my eigenvalues that are real. You can also find some complex eigenvalues, but I can at least find some real eigenvalues. And so to prove that, I think what I'm going to do is first prove a little lemma. So I probably shouldn't be writing this like inside of the proof, but it's fine. We know what we're doing. And I'm going to say, well, what would it take to get real eigenvalues? So do you guys know this fact? Like, when does a matrix have real eigenvalues? Yeah, it's fine if you don't. It's not like, these are things you should know about the world. Right, that's exactly right. Good. Okay. So A has, A is some, let me just step back to the complex case. So if you have some matrix, I'm just going to prove it's something a little more general than we need, but it's a good fact for you to know about the world. It's like, you've seen these like man on the street interviews where they're like, find Canada on a map. And people like pointing at Brazil or whatever. Well, now you're ready. So if someone comes up and they're like, when does a matrix have real eigenvalues? You don't want to be the idiot who's like, oh, I don't know, maybe if it's skew symmetric or something. No! It's like, A has real eigenvalues when A is Hermitian. And let me just remind you what Hermitian means. That just means that A conjugate transpose is equal to A. This is a special class of normal, right? If you're Hermitian, then you're normal. So this is a special class of, if you have the spectral theorem, this is true for all normal matrices. But if you happen to pick a matrix that's Hermitian, where A conjugate transpose is A, then you'll end up with your diagonal matrix being real. You may not have your unitary matrix as real, right? We'll have to argue in a second why, if in fact you go to symmetric. But so Hermitian is a special case of being normal. So like maybe just to make this clear, if you're symmetric, that's saying that A transpose equals A. That's a special case of being Hermitian. Right, that's saying that A conjugate transpose equals A. So this is the restriction that your matrix is real. And then you come down here and you're like, okay, well, if your matrix is real, you move here. But you might have a complex matrix that's Hermitian but not symmetric, right? And then you come down, like if you have imaginary entries or something, right? If you have a non-zero imaginary part, being Hermitian wouldn't be the same as being symmetric. So I guess I should be saying like, okay, when I say symmetric implies Hermitian, that's not entirely true now, is it? I'm saying that if A is real, if A is real, then being symmetric implies you're Hermitian, right? But in general, being Hermitian implies, for any matrix, complex entries, implies that you're normal. Because A conjugate transpose A is equal to A conjugate transpose. Okay. If this is a complex matrix, you could be Hermitian and not symmetric. So maybe this was not like the best way to write this because it might throw you off if you're thinking, and I'm proving it right now of complex matrices. But in a second, it's just going to collapse to symmetric matrices when we restrict ourselves to only real matrices. Okay. So here we go. So A has real eigenvalues whenever A is Hermitian. And probably shouldn't have put that there because now I'm letting myself think about complex matrices. So here's my proof. Let's just say you have some eigenvalue, lambda, with some corresponding eigenvector, v. So I'm just saying that A times v is lambda v. And in principle, v could be complex. Lambda, in principle right now, a priori is complex, right? We don't know if the imaginary part is 0 or not. But here's what we can say. If I take lambda and I multiply it by the magnitude of v squared, I'm going to make these little arrows because I don't want to confuse the vector bar with the complex conjugate, which I'm going to do in a second. Since V is a matrix with complex entries, this magnitude is the same thing as V conjugate transpose times V. That is the complex conjugate of V dotted with itself, right? It's not just V dotted with itself, but for complex numbers, you have to do the complex conjugate. But since this is a scalar, you can slide him wherever. So I could slide him to be next to my V, but I know lambda V is the same thing as AV. So this is the conjugate transpose of V times AV. And now let's use the fact that my matrix A is Hermitian. So that A is equal to the same thing as the complex conjugate of V times the complex conjugate of A times V. Well, I guess there are two ways you can see this. One way is, since these are both complex conjugates, I can now just factor out the complex conjugate, but that means I need to reverse the order. So now this is AV complex conjugate times V. But AV is, since V is an eigenvector, it's just lambda V complex conjugate V. But here I have a scalar that I'm multiplying my vector by and then taking the complex conjugate. So my scalar lambda is going to become the complex conjugate of lambda. So this is just the complex conjugate of lambda times V complex conjugate V, which is just the complex conjugate of lambda times the magnitude of V squared. But V is an eigenvector, hence it's non-zero. You know, if this was 0, you would just get 0, right? So this is some non-zero eigenvector. So hence we conclude that lambda equals lambda bar. That is, lambda is equal to its complex conjugate, which means lambda is real. If it had any imaginary part, it would have changed sign. So that completes the proof. Okay. Doesn't give us that V is necessarily real. V could be still some complex vector. But as long as you're Hermitian, you're going to have that your eigenvalues are real. So if we go back to our setting of our proof, our overall proof, so that ends this little mini proof within my lemma. So if we go back to what we're trying to show, we're saying A is symmetric with some real values. So then, of course, A is Hermitian. And so then that gives you that all of the eigenvalues of A are real. So by lemma, since our A is symmetric, we have that D must have real values. Okay. So we're almost there. Now, the last thing we want to argue is that U is also going to be real. We have that my D has real value entries. Now I want U to have real value entries. So let's think about this. So let's say, so let's just consider some. So suppose lambda, which we know is a real number now, is an eigenvalue for A with some corresponding eigenvector, V. I guess I want to say that the V is real, but that's actually not true. It's not true. You might have V having complex entries. So what I really want to do is I want to argue, well, there's a way to construct another eigenvector for lambda that does have real entries. You might have some eigenvector for lambda that has complex entries. But I want to say, well, there's a way for us to build an eigenvector for lambda that has real entries. And then we can just pick the eigenvectors that are real, and we'll get for free that they're orthogonal to each other, just like we did before. And so then you can just scale them down so that they're all norm 1. And then you have an orthonormal basis of real eigenvectors. So how can I turn this V, that's a complex vector, into a real vector and keep it as an eigenvector? Well, my first observation is I want to claim if V is an eigenvector, then the complex conjugate of V is also an eigenvector for lambda. An eigenvector of A for lambda. So why is that true? Well, we're given that A times V is lambda V, and I know A is symmetric. So how am I going to get this claim? Well, I guess we don't just have that A is symmetric. We also have that A is real, right? We have that A is a real symmetric matrix. So what that means is if I take the complex conjugate of this entire thing, it's the same as taking the complex conjugate of the entire thing on the left. But the complex conjugate of AV is the same thing as the complex conjugate of A. The complex conjugate of A is just A, and the complex conjugate of V. And then lambda is also real. You actually just need the A is real, and lambda is real. So the complex conjugate of lambda is just lambda. And then the complex conjugate of V is the complex conjugate of V. So once you have that your A and your lambda are real, you immediately have, if V is an eigenvector, then the complex conjugate of V is also an eigenvector for the same lambda. Yeah? because taking the complex conjugate of A and lambda leaves it unchanged because they're both real. So now I have two eigenvectors for lambda, V and V complex conjugate. So from those, can I build one that's real? What, how? Do what? Great, add them. So then note, if I just do V plus its complex conjugate, I could also do minus, by the way, but if I just add them, well, that's going to be real because you have A plus BI, right, plus some A minus some BI, and then you just get 2A. So this is 2 times the real part of the vector. So this is now spanning Rn. But if V and V complex conjugate are both eigenvectors, you have that A times V plus V conjugate is just AV plus AV complex conjugate. And since these are both eigenvectors for the same eigenvalue lambda, that's just lambda V plus lambda V complex conjugate. So that's just lambda times V plus V complex conjugate. Hence, V plus V complex conjugate is an eigenvalue. Okay. So this is really just, you can scale it by a half, and then you just have the real part of V. Right? Whenever V is an eigenvalue for a real matrix that has a real eigenvalue, the real part of V is also an eigenvector, as is the imaginary part. So that completes the proof. I mean, think about it. Your U is just some collection of eigenvectors. If they're not real, I'm just giving you a process to change them into real ones, right? They're orthogonal to each other. Scale them if you need to make them all unit length. And now your U will also be real. Okay. So a lot went into here, but all you need to remember is that in general, if you have a complex matrix, when you break it down using your spectral theorem, your diagonal and unitary matrices may be complex. If your matrix wasn't just normal, but it was in fact Hermitian, well now, instead of D being complex, you guarantee your D to be real entries. But if you want to start out with a matrix that's real and make sure D and the unitary matrix are both real, you need to begin with a symmetric matrix. And so this is called the real spectral theorem. Okay, so we'll stop there for today, and we'll continue to talk about other decompositions next week.